All right, welcome to The Explainer. I am absolutely thrilled to have you here today. Look, our goal for this session is simple. We are going to completely strip away the intimidation factor of physics. If you've ever looked at a textbook chapter on kinematics, the study of motion, and just felt a wave of dread, well, you are in the exact right place. Today, we're breaking down those foundational class 9th concepts of how and why objects move. And we're going to do it using clear, everyday ideas. So let's just dive right in.
First up, I have a question for you. Are you moving right now? If you're sitting in a chair watching this explainer, you might instinctively be like, no, obviously, I'm perfectly still. But are you? I mean, relative to the chair, sure, you're stationary. But relative to the center of the Earth, you're actually spinning. And relative to the sun, you are literally hurtling through space at thousands of miles per hour. This brings us to our very first foundational rule of physics. Motion is entirely relative. It completely depends on the observer's reference point.
So here is our roadmap for today. We'll be hitting distance and displacement, speed and velocity, acceleration, motion graphs, the equations of motion, and finally, we'll wrap things up with circular motion.
All right, let's jump right into part 1, distance, displacement, and motion.
Imagine you're mapping out a quick trip from your home to the grocery store. In everyday life, we tend to use words interchangeably that actually mean vastly different things in physics. Take distance. Distance is the actual physical journey you took. It accounts for every single twist, turn, detour, and winding road you traveled. It's the total length of the path. But displacement? Displacement really doesn't care about your detours. Displacement is the ultimate shortcut. It is strictly the shortest, straightest line from your starting point directly to your final position, along with the direction you went. To put that into perspective, picture this. You decide to run a grueling 10-kilometer race on a track. You are sweating, your muscles are absolutely burning, and you finally cross the finish line, which, on a track, happens to be the exact same line where you started. You undeniably ran a distance of 10 kilometers. But physics looks at you and says, hey, your start and end points are the exact same, so your displacement is absolutely zero. All that immense physical effort, and purely in terms of displacement, you went nowhere.
Moving right along to section 2, speed and velocity explained.
Imagine you're sitting behind the wheel of a car. Speed is exactly what you see on your dashboard speedometer. It just tells you how fast you're eating up distance over time. 60 miles per hour, boom, that's it. In physics, we call this a scalar quantity, meaning it only has a magnitude or a size. But velocity? Well, velocity is basically your speedometer combined with a compass. It's how fast you're going and in what specific direction. 60 miles per hour due north. That makes it a vector quantity. Speed is just the pace, but velocity is the pace with a destination in mind.
Okay, on to section 3, acceleration, changing the pace.
Think about that feeling of stepping hard on a gas pedal. Acceleration is simply the rate of change of velocity per unit of time. Now, the absolutely crucial point here is that acceleration isn't just going fast. It just means your velocity is changing. And remember, we just learned that velocity is speed and direction. This means, sure, you're accelerating if you speed up, but you are also accelerating or decelerating if you hit the brakes and slow down. And, remarkably, you are mathematically accelerating if you keep the exact same speed but simply turn the steering wheel to change direction. Any change in velocity over time is acceleration.
Next up, section 4, visualizing motion with graphs.
So, let's shift gears from the feel of motion to the look of it on paper. Now, I know, these charts can look a little dense at first glance, but let's guide our eyes through them together. These graphs are how physicists map out an entire journey at a single glance. By putting time on the bottom x-axis and either distance or velocity on the vertical y-axis, all that abstract movement we just talked about gets translated into a single clean line. You can literally look at the slope of these lines to immediately know if an object is moving steadily, standing still, or speeding up. Let's make those abstract lines real. Here is a super simple cheat sheet for a standard distance time graph. If you see a perfectly flat horizontal line, it means distance isn't changing as time ticks by. That means the car is parked, it's stationary. But if you see a straight diagonal line angling upward, that means distance is increasing at a perfectly steady rate. The car is basically cruising down the highway on cruise control. Once you lock in these simple rules, you can read the story of any object's journey just by looking at a line.
All right, we have arrived at section 5, the equations of motion.
Now, don't let the math scare you. These 3 foundational equations are basically a physicist's ultimate toolkit. In these formulas, u is your starting velocity, v is your final velocity,
A is acceleration, T is time, and S is displacement. If you know just a few of these pieces of information about an object, you can use this cheat sheet to mathematically predict its exact future. You can figure out exactly where a moving object will be or how fast it will be going at any given second. It's essentially a superpower.
And finally, Section 6, Uniform Circular Motion.
Okay, time for a bit of a curveball. Up until now, we've mostly been thinking about things moving in straight lines. But, as you know, the universe doesn't just move in straight lines. Uniform circular motion is the motion of an object traveling in a perfectly circular path at a constant, unchanging speed. Think of a satellite orbiting a planet, or actually even just a rock tied to a string swinging around your head at a steady rhythm. Take a second to process that image of a perfectly steady circular path.
Because here is where this concept completely breaks our intuitive brain. Remember our definition of velocity? It's speed and direction. And our definition of acceleration? Any change in velocity. So, if an object is moving in a circle, its speed might be perfectly constant. But to physically trace out that circle, its direction has to continuously, microscopically change at every single moment. Because the direction is always changing, the velocity vector is always changing. Therefore, an object moving in a uniform circle is absolutely always accelerating, even though its speed never goes up or down. It is such a beautiful, mind-bending fact of physics.
Which brings us to our final thought for this explainer. Think about the very planet we live on. The Earth is in near uniform circular motion, constantly changing direction to stay in orbit around the Sun. That means the Earth, and everything on it, including you and me, is in a state of constant acceleration, right this very second. So I'll ask you again, are we ever truly at rest? It's a fascinating question, and it really proves that physics isn't just a bunch of textbook formulas, it's the hidden framework of our entire reality. Thank you so much for joining me on this explainer. Keep questioning the world around you, and I'll see you next time.